All right, let's do some math on sound and just waves in general. So let's start with this. Dolphin hunts for dinner. Dolphin sends out sound with a frequency of 8,000, and it takes 4.8 seconds for the echo to be heard uh, by the dolphin itself. The speed of sound in water is 1,500 meters per second. First one is what's the wavelength? So there's two equations we're going to be working with. Velocity is your distance over time. Velocity is your wavelength times your frequency. In both of these, the velocity would be 1,500 meters per second. So if I want wavelength, I want this, lambda. V is lambda f. 1,500 equals lambda times 8,000. So grab a calculator, 1,500 over 8,000. I get a wavelength of 0.1875 meters, or about 19 centimeters. Now it says, if the wave enters the atmosphere and is heard on board a boat, what's the wavelength of the sound? This is a huge idea in all waves. Frequency is the fundamental property of the wave. Okay? So, I spelled fundamental wrong. That's fun. Fundamental. Okay. Back to our task. The point is the frequency in water equals the frequency in air, which in this case is 8,000. So the speed of the wave has changed to 343, but the frequency is still 8,000. So when using V equals lambda F, 343 equals lambda times 8,000. People might be saying, how did I know the speed was 343? Because I've been doing this for a very long time. 343 is the standard accepted sound of speed in air at STP. The wavelength is 0.04288 meters. Our next question asks, how far away from the dolphin is dinner? So the sound wave was traveling for 4.8 seconds. I can do this in one of two ways. I can cut that 4.8 in half, or I can solve velocity is distance over time. 1,500 equals distance over the 4.8. But it's important to note going this route, what I've actually solved when I've solved the distance is how far did the wave travel? In this case, the wave traveled 7,200 meters. Now, that means if here's my dolphin and here's a dinner, the fish, the wave travels, boom, bounces off, and comes back. So I've essentially double counted. Dinner will be 3,600 meters away. Let's take a look at the second one. A freshman is scared of a thunderstorm because they're freshmen. At home all by himself, the poor little freshman sees a flash of lightning, counts to 7, hears the boom of the thunder. How far away is the lightning strike? So that's the speed. And then we see 7 seconds, that's time. Velocity is distance over time. 343 equals the distance over 7. Our freshman is about a mile and a half away from that lightning strike. Our last one. It doesn't matter if we're talking sound or light or any other wave. The rules are the same. Velocity is lambda f. Velocity is distance over time. So, in this particular example, we see in order to protect Michigan from the Buckeyes down south, Paul Bunyan takes up patrol along the border. We have his red shirt at 700 nanometers and his blue ox at 4,200 nanometers. Sorry, 420 nanometers. So let's focus on the red shirt. Now you see nanometers. You're going to want to get used to this. 700 nanometers, that's 700 times 10 to the negative ninth, or 700 e negative 9. The speed of light is 3 times 10 to the 8th meters per second. So if I want to find the frequency of his blue flannel shirt, of his red flannel shirt, V is lambda F. 3E8 equals 700 E negative 9 F. So take a calculator, go 3E8 divide 700 E negative 9, and I get a very high frequency, 4.29 E14 hertz. For colors, the frequency is in the hundreds of trillions. So you should be looking around E14s. Blue, the ox, lambda, 420 nanometers. That's 420 E negative 9. The velocity is still 3 times 10 to the 8th. So 3E8 equals 420 E negative 9 F. So 3E8 divide 420 E negative 9, 7.14 E14 hertz. That's a wrap.